Almost every solar panel bolted to a rooftop anywhere on Earth right now depends on one material, and that material has a serious problem nobody in the solar industry likes to talk about. It is silicon. To turn raw silicon into something that can actually generate electricity from sunlight, manufacturers have to heat it to over 1400 degrees Celsius, purify it to an almost unbelievable level of chemical cleanliness, and slice it into wafers so thin they can shatter if you look at them wrong. That process is expensive, it is energy intensive, and after nearly 70 years of refinement, silicon solar cells have run into something physicists call a hard ceiling. There is a maximum theoretical efficiency a single layer of silicon can ever achieve, no matter how good the manufacturing gets, and the industry has been creeping toward that ceiling for years. But in a laboratory in Beijing, a team of chemists just published a solar cell that does not rely on that traditional silicon wafer process at all, and in independently certified testing, it did something silicon alone has never managed to do. If this technology scales the way its creators believe it can, the silicon solar panel that has defined the entire renewable energy industry for decades could become the expensive, outdated option. This is not a concept render or a press release full of promises. It is a peer-reviewed result published in the journal Nature, verified by outside labs, and it is forcing solar engineers around the world to rethink what a solar panel is even made of. If you are enjoying videos like this, please hit the like button, because it takes a lot of effort to make these, and subscribe so you do not miss the next one. To understand why this matters, you first need to understand the wall that silicon has been running into for years, and why an entirely different class of material has become the most closely watched technology in the solar industry. Silicon solar cells work by absorbing sunlight and using that energy to knock electrons loose, creating an electrical current. The problem is that silicon can only efficiently absorb a fairly narrow slice of the light spectrum that reaches the Earth's surface. Blue light, red light, infrared light, they all carry different amounts of energy, and a single layer of silicon is simply not built to capture all of it efficiently. Physicists have known about this limitation since the 1960s, when two scientists named William Shockley and Hans Queisser calculated the absolute maximum efficiency a single-layer silicon solar cell could ever theoretically reach, a number that sits right around 33.7%. For decades, that number has functioned almost like a law of nature for the solar industry. You could refine manufacturing, improve purity, tweak the cell architecture, but you could never punch through the Shockley-Queisser limit with silicon alone, because the physics simply would not allow it. This is where a different material family enters the story, and it starts with a mineral discovered in the Ural Mountains of Russia back in 1839. A geologist named Gustav Rose found a strange calcium titanium oxide mineral and named it after a Russian mineralogist called Lev Perovskite. For over 150 years, perovskite was little more than a geological curiosity, a crystal structure that showed up in textbooks and not much else. Then, starting around 2009, scientists discovered that synthetic versions of that crystal structure had an extraordinary and completely unexpected talent. They could absorb sunlight and convert it into electricity almost as efficiently as silicon, but they could be manufactured using simple, low-temperature liquid coating processes instead of superheated furnaces and ultra-pure wafer slicing. You could essentially print a perovskite solar cell the way you print ink onto paper, at a tiny fraction of the energy cost of manufacturing silicon. The real breakthrough potential of perovskite was never really about replacing silicon outright. It was about stacking on top of it. Because perovskite and silicon absorb different parts of the light spectrum, researchers realized you could layer a perovskite cell directly on top of a silicon cell, creating what is called a tandem architecture, and let each layer capture the wavelengths of light the other layer misses. In theory, that stacked approach could smash straight through the Shockley-Queisser limit, because you are no longer bound by the physics of a single material. Multiple labs around the world chased this idea for years, and by 2024 a company called Oxford PV had pushed a silicon perovskite tandem cell to a certified 33.9% efficiency, technically exceeding the theoretical ceiling for silicon acting alone. It was a genuine milestone, but it still depended on silicon as half of the equation, which meant it still carried a large portion of silicon's cost and manufacturing complexity. The team that just made headlines took a different and considerably bolder path. Researchers at the Institute of Chemistry at the Chinese Academy of Sciences, led by a scientist named Meng, built a tandem solar cell that pairs a perovskite top layer with an organic material bottom layer, removing silicon from the equation entirely. Published in the journal Nature, their device achieved a certified steady-state power conversion efficiency of 28.04%, with a peak laboratory efficiency reaching 28.80%. On its own, that number sits below what the best silicon perovskite tandems have managed. But the significance of this result has nothing to do with beating the absolute efficiency record. It has to do with proving that a completely silicon-free tandem architecture can perform at a genuinely competitive level, using two materials that are both dramatically cheaper and less energy-intensive to manufacture than silicon ever was. The specific engineering problem the team had to solve is the same one that has haunted perovskite research for over a decade, and it is the reason perovskite solar cells still are not sitting on your roof today. Perovskite crystals are chemically unstable. Expose them to heat, humidity, or prolonged sunlight, and the crystal structure can degrade, causing the cell's performance to collapse over months rather than the 25-year lifespan silicon panels routinely deliver. Meng's team identified a specific culprit inside their wide bandgap perovskite layer, a molecule they call TDB, which under light exposure transforms into a new molecular structure called TAB. That transformed molecule anchors itself precisely at the grain boundaries of the perovskite crystal, and in doing so it suppresses the movement of halide ions and prevents phase separation within the material, two of the primary chemical processes that cause perovskite cells to degrade over time. In the researchers' own words, the molecule shifts from being light-averse to light-adaptive, meaning the very sunlight that used to damage the material now actively helps stabilize it. In testing, the device retained 90% of its original efficiency after 625 continuous hours of operation under a standardized international stability protocol, a meaningful improvement over previous silicon-free perovskite attempts, though still short of the multi-decade durability that makes silicon the trusted default for permanent rooftop installations. This breakthrough did not happen in isolation. Chinese research institutions have been producing a genuinely startling pace of perovskite records over the past 2 years. Researchers at the University of Science and Technology of China hold the current certified record for a single-junction perovskite cell at 26.7%, verified independently. A separate Chinese Academy of Sciences team based at the Ningbo Institute of Materials Technology and Engineering published an all-perovskite tandem cell in the journal Nature Nanotechnology, hitting a certified 30.3% efficiency in rigid form and 28.0% in a flexible version, a result significant enough that Chinese manufacturers are now moving toward gigawatt-scale pilot production lines for the technology, years ahead of where most Western analysts expected commercial perovskite manufacturing to begin. It is important to stay honest about where this technology actually stands, because that honesty is exactly what separates a real scientific milestone from marketing hype. No major manufacturer anywhere in the world is shipping a fully commercial silicon-free perovskite solar panel in 2026. The efficiency numbers coming out of Chinese labs are extraordinary, but they were achieved on small laboratory cell areas, often around a single square centimeter, while a real rooftop solar module needs to maintain that same uniform performance across 1.5 to 2 square meters of surface area, a manufacturing challenge that has tripped up nearly every perovskite lab result that came before it. Durability remains the single biggest question mark. Heat causes the organic components inside these cells to break down. Moisture can penetrate the crystal lattice. Companies including Oxford PV, Longi, and Hanwha Q cells are all targeting commercial production windows sometime between 2026 and 2028, but every one of those timelines has already slipped once, and the gap between a peer-reviewed Nature paper and a bankable 25-year product warranty is where most promising solar technologies have historically gone to die. But every genuine shift in solar technology has followed roughly the same path. The first practical silicon solar cells built at Bell Labs in 1954 converted barely 6% of the sunlight that hit them and cost a fortune to manufacture. It took decades of incremental engineering, not a single miracle breakthrough, to get silicon to where it sits today. What Meng's team in Beijing has done is take a material that was, for over 150 years, nothing more than a mineral curiosity in a Russian mountain range, and push it to the point where it can credibly compete with technology the entire global energy industry has spent 70 years perfecting. They did not just chase a bigger efficiency number. They solved one of the specific chemical failure points that has kept this entire category of technology stuck in laboratories, and in doing so, they proved that the next generation of solar power might not need silicon in the equation at all. There is something worth sitting with here. Every rooftop solar panel currently generating power somewhere in the world represents the endpoint of nearly 70 years spent perfecting a single stubborn material. And now, a molecule that only exists because researchers in Beijing figured out how to make sunlight repair the very damage sunlight causes might be quietly building the thing that finally moves the industry past it, not with a louder headline, but with a steady climb of certified numbers, published one careful paper at a time. So here is a question for you. If a silicon-free solar panel reached your local hardware store at half the price of what is on your roof today, would you switch? Let me know in the comments.